Hello, welcome to this video on heterocyclic chemistry. In this video we will look at 6-membered aromatic heterocycles, pyridines, with oxygen substituents around the ring. So if we try and put an OH group on a carbon of pyridine, there's 3 different ways we can do that. We can put it at the 2 position, or we can put it at the 3 position, or we can put it at the 4 position. Now, the introduction of the oxygen with its lone pair makes the aromatic ring more electron rich. But what's interesting now is that we can have tautomerization for some of these arrangements. So in the 2-hydroxypyridine, the oxygen-hydrogen bonds can move to be a nitrogen-hydrogen bond. This is not possible in the 3-hydroxypyridine, but is again possible in the 4-hydroxypyridine. This alters the properties of the ring so that now the amine is less basic because it is a little bit like an amide. If we want to look at the mechanism in detail, there are 3 different ways in which we can add our OH to our pyridine ring. 2, 3 and 4 position. And we can draw the hydrogen migrating from the oxygen to the nitrogen. So we swap a OH bond for an NH bond and an NC double bond for an OC double bond. We can see we can push the arrows around the ring in such a way that this is possible with the 2 and 4 substituted hydroxypyridines. These molecules with the carbon ion are called pyridones. But when we go to our 3 substituted compound, this is not possible. So because we have these electron-rich groups on our ring, we'll see that a lot of reactions which were difficult before, for example nitration, become a lot easier. And so now we can see here, we get nitration of 4-hydroxypyridine using our standard nitrating conditions, that is sulfuric acid and nitric acid. Before we had to heat this reaction with just pyridine to 300 degrees and we got 6% yield, whereas here the yield is much better and the temperature is only 100. We can swap that OH group for a halogen atom if we use one of our usual bunch of phosphorus reagents, and that proceeds by attack of the oxygen onto the phosphorus bond. This makes the OH is a bad leaving group, but phosphorus activates the O to be a good leaving group, and one of the chlorines that was released comes back in and does a displacement to give our new carbon-chlorine bond and kick out the oxygen to create a very strong phosphorus-oxygen double bond. This is useful because obviously we can maybe exploit the OH reactivity and then swap that for a chloride, which we can use in substitution or lithiation reactions, or maybe cross-coupling. We can look at this in more detail. We have our pyridone form. So we're going to draw the 2 pyridone here, so our carbon atoms on the 2 position. We can draw the mechanism of either pyridine or pyridone or hydroxypyridine forms. And we have our PCl5 reagent. And now this amide portion of the ring is going to react via the oxygen to create a new phosphorus bond, and that's going to give the loss of a chloride from the phosphorus, and chloride is a good leaving group. We could have drawn the OH from the hydroxy attack the phosphorus directly as well. Now at this stage what we've done is we've turned OH, which is a bad leaving group, into an OP, which is a good leaving group. So the chloride that we displaced can come back in, and we can then get loss of the oxygen, and that's driven by the formation of a strong phosphorus-oxygen double bond. And this is a general strategy. If we have this kind of motif within various different heterocycles, we can use this to install a chloride. And we saw this as well in the Vilsmeier reagent. Now, I did say there's 3 different ways in which you could put an oxygen around the ring, but that's only if you wanted to attach it to carbon. You could also have an oxygen on the nitrogen. We've seen several times that the most important nucleophile in pyridine is its lone pair. And if we treat that with an appropriate oxidizing agent, such as MCPBA, we can introduce an NO bond. This gives a permanent negative charge on the oxygen and a positive charge on the nitrogen, and this is called a Pyridine N-oxide. We have an oxidation at the N position. We can also break that bond, so heteroatom bonds are quite weak, and so if we heat our molecule with triphenylphosphine, then we will get the phosphorus breaking the weak bond, driven again by that strong phosphorus-oxygen double bond. We can look at the mechanism in more detail. So our most nucleophilic part is the lone pair. That lone pair isn't in the aromatic system. It's in an sp2 orbital. So it can break the weak oxygen-oxygen bond in MCPBA. And that gives us the new nitrogen-oxygen bond with a negative charge on the oxygen and the positive charge on the nitrogen. And if we want to reduce that bond, we can use something like phosphorus. Phosphorus has very strong double bonds with oxygen, so it's a strong driving force for this reactivity. And so it will take the oxygen away from the nitrogen and give us back our pyridine. So what effect does this have on the reactivity of our system? Well, now what we have is that electron-rich oxygen next to the ring with its negative charge, and it can donate electron density into the ring, so that now our previously electron-deficient pyridine system becomes more electron-rich. And in fact, we can see the oxygen overrides the selectivity of the pyridine. If this was a pyridine, we would have nitration at the 3 position, but because we have the oxygen, we now get nitration at the 4 position. Of course, if we wanted a 4-nitropyridine, we could then reduce it down using triphenylphosphine. But as well as being more nucleophilic because of the oxygen, now our heterocycle has a permanent positive charge on it. So it's more electrophilic as well. So in this substitution reaction, we have now got that permanent positive charge, which means that when our methoxide adds in to displace the chloride, the reaction is faster. And again, if we want the pyridine version, we can reduce it using triphenylphosphine. We can go through these mechanisms a little bit more slowly. So here's our Pyridine N-oxide, a positive charge on the nitrogen, negative charge on the oxygen. And if we have the nitronium cation, remember we make that by the dehydration of nitric acid by a stronger acid like sulfuric acid. We can push the arrows through from that oxygen negative charge. We'll break the aromaticity and make a new carbon-nitrogen bond. And then to regain the aromaticity in this electrophilic aromatic substitution reaction, we lose H+, and we can see now how that oxygen directs nitration at the 4 position. As well as being more nucleophilic, our system is now more electrophilic. We have a permanent positive charge on that nitrogen, which means if we do some kind of nucleophilic aromatic substitution with methoxide. We can draw an attack at the chloride, pushing the arrows around to neutralise that positive charge. We break the aromatic ring temporarily, but then we use the nitrogen lone pair to push electrons around the ring, lose chloride, our good leaving group, and restore our aromatic system. The N-oxide can also be a protecting group because, as we've seen, that lone pair is the most reactive nucleophilic part of our pyridine system. But that can be a problem. If we want to do something like a palladium reaction, nucleophilic lone pairs mean that our pyridine could act as a ligand for the metal. And we know that for palladium chemistry, we like phosphine ligands. And pyridine ligands can shut down the reaction completely. So here you can see the difference between a cross-coupling of N-oxide and a normal pyridine, and the N-oxide reaction is much, much faster and gives a higher yield over a shorter time. And this is a combination of the fact that the nitrogen lone pair deactivates the catalyst by coordination, but also because oxidative insertion into electron deficient systems is faster, and the top example, the N-oxide, now has that permanent positive charge on the ring. So, overall, we've seen that addition of an oxygen substituent, an OH, makes the system more electron rich, but if that's in the 2 and the 4 positions, this lets us enter 2 different tautomers where we get the hydroxy and the carbonyl forms. We can convert OH groups to the corresponding halides using a phosphorus halide reagent. And we can also have an oxygen on the nitrogen. We can oxidize pyridines with MCPBA to give the pyridine N-oxide, and we can reduce them back to the pyridine with triphenylphosphine. The pyridine N-oxides become good nucleophiles and electrophiles, and also this can be used as a strategy to protect the nitrogen lone pair. Thanks for watching, see you next time.